time for us to do some more practice doing improper integration, which is not really so improper. It's really saying, hey, let's make sure we're careful and not rush anything. Pay attention to infinity. It's also a great chance to do a lot of practice with other techniques, because really improper integration is just various integration problems where there's an infinity that happens to be involved, which may or may not play a significant role in finding the answer. Well, as with all things, it's important to do practice. The more that we practice, the better we become. And we want to be really good. We want to be fantastic. And so you need to make sure you do as much practice as you can. If you're following along, make use of the pause button. If you see a problem, try it yourself first. See how far you can get. And if you ever need me on any problem, just unpause me. We can work it out together. Well, let's begin. Our first problem. Evaluate the integral negative infinity to 0 e to the 1 over t squared dt. Okay, well, this doesn't seem so bad, right? So what did we do? Now remember, when we're talking about improper integrals, it's a lot of the same ideas, right? So we see it's an improper integral because there's an infinity involved. It's actually doubly improper because look at 0. See, at 0, we have like a t squared downstairs. Ooh, that's bad. That's going to get us into trouble because we're dividing by t squared. And so, well, it's very improper, doubly improper, right? But for right now, let's just say, suppose we didn't have to worry about the improper integrals, and we just solved this problem, the integral of e to the 1 over t squared. What would we do? Well, we look at it and say, hey, we see that 1 over t function inside the exponential function, and the derivative of 1 over t happens to be minus 1 over t squared, which is sitting right there, almost as if it was planned that way. So let's try to do substitution. All right, so the idea, if we let u equal 1 over t, then our du would be minus 1 over t squared dt. All right, so far seems pretty harmless. And we can even move the minus sign across, so that'll become plus, becomes minus. All right, now let's think about what's happening. Well, that t squared dt becomes a minus du, the e to the 1 over t, e to the u. And now we got to pay attention to the bounds. And this is the part where we got to be a little bit slow. We don't want to rush into it. Let's talk about our bounds. Let's start with our lower bound. So here we're saying t is negative infinity. Of course, is in quote marks, because negative infinity is not a number. We can't just be like, oh, it's the number negative infinity. No. Can't do that. Can't do that. So what do we mean? Well, when you see an infinity in the bounds, it's like as we go to infinity. So it's really more of a process than it is a destination. So with that in mind, we say, okay, if we want to say what do the new bounds become, well, we say, well, what happens as we go to infinity? In particular, what happens to u? Well, as we go to infinity, well, we're going to go to 1 over a large negative number. But 1 over a large number, positive or negative, goes to 0. All right, now the upper bound. And this one is another one where we don't want to rush ourselves. The question, what does the upper bound become? And it's not so trivial. A lot of people would say, hey, 1 over 0 is infinity, woohoo, and be done. But we're not a lot of people. We like to take our time to savor, to reason about what's going on here. So, in this case, what's going on? Well, notice that we're integrating from negative infinity to 0. And 0, it's a point of improperness. So, if we're thinking of our number line, and here's our 0, so we're going along here. When I plug in 0, what I really should think of is what happens as I'm going to 0. All right, so how are we going to 0? The answer is we're coming to 0 from below. So we're coming to 0 from the left-hand side. All right. Well, why is that important? Well, that says really we should think of, we don't plug in 0. We say, well, we're getting closer to 0 in the negative direction. So it's 1 over a small negative number, which means what? Well, it's going to be a large negative number. And so our new bound updates to minus infinity. All right, so that's important to keep track of that. So that's a little bit of subtlety there, right? We want to pay attention. So there's kind of a hidden sort of limit that we've done here, where the limits are how do we deal with the bounds. Now we can make this cleaner, because certainly we think of 0 as being larger than minus infinity. We can even get rid of the minus sign. So you can say, okay, look, this is the integral minus infinity to 0 of e to the u du. All right, well, great. We can do that. The integral of e to the u is e to the u. And then we're going to evaluate minus infinity to 0. Well, plug in e to the 0, you get 1. Now, when we plug in, okay, so what do we mean by plug in? So really, if we're being formal, we would say minus the limit as u goes to minus infinity of e to the u. That's what we mean by plug in minus infinity, saying what happens as we go to minus infinity. And the nice thing is we know what happens to the exponential function. An exponential function, where we have like e to a very large negative number, it's going to get smaller and smaller and smaller. It's going to go to 0. So we end up with 1. Now, oftentimes we don't write this out because we say, oh, we see what the behavior is, and here's what happens, and we're done, right? But if we didn't see what the behavior was, well, we can still write things out and be a little bit more formal, and that's all right. No problem with sometimes being a little bit more formal. All right, well, nice warm-up problem. On to our next problem. Okay. Find the integral from -1 to +1 of 1 over x to the 2/3 dx. Well, now at first glance we say, look, there's no problem, right? There's -1, there's +1. There's no problem with the function at -1, +1. But there is a problem somewhere in the middle. So we have to be careful here. So if you plot x to the 2/3, or rather I should say x to the minus 2/3, what ends up happening is your function has an asymptote at 0. So we're going from -1 to +1, and so we have this little part that's blowing up in the middle. So there is an infinity involved, which means there's an improper integral here. And of course that means we're going to be careful. We want to be careful. So what does being careful here mean? Well, what it means is we should really break this up into pieces. So we talk about -1 to 0 of 1 over x to 2/3. And we talk about 0 to 1 of 1 over x to 2/3. But here's a place where we can justifiably use symmetry and say, hey, this is an even function so that it flips over in a nice way. So what happens on the positive side, same thing happens on the negative side. So these two pieces will be equal to each other. Okay, so let's just double the integral 0 to 1, and here x to the minus 2/3 dx. Now, if we were being very, very formal, so we should do it at least once. We should be formal at least one time because we're being very informal on most of the problems. We say, okay, what's the problem? Well, the problem here is 0. All right, so how do we deal with it? Well, the way we deal with it is we say, okay, we're going to take our limit as we go to 0 from above and integrate b up to 1 of x to the minus 2/3 dx. So picture-wise, it says, look, we're just going to take this piece right here. We go from b up to 1. Now, why that part? Well, because we don't have that infinity that we have to deal with, because we stop before we blow up. And so we say, hey, this is a perfectly fine function. So this would be 2, and we have the limit as b goes to 0 from above. And this integral, well, would be what? You add 1 to the exponent, that's x to 1/3. Multiply by the reciprocal, that's 3. And evaluate b to 1. So, great. You can even pull out the 3. So we get 6. When as b approaches 0 from above. And when you plug in 1, you get 1. And then subtract, plug in b. b to the 1/3. And now we're like, hey, we can see what's happening. As b goes to 0, b to the 1/3 goes to 0. Positive exponent. So we end up with 6. And all right, good, we're done. Woohoo! All right, so that's if we had been very formal. Now, oftentimes we would just say, well, let's just integrate. And we say, okay, well, that'd be 3x to 1/3 from 0 to 1. No problems. Everything's good. And really, as long as your endpoints are fine, there really are no problems, and everything's good. Now, you might have said, well, Steve, I tried this problem, and I did the following. I said, this is just integral from -1 to 1, x to minus 2/3 dx. Well, that's integrate 3x to 1/3. Evaluate from -1 to 1, which becomes, when you plug in 1, well, 1 to the 1/3 is 1, and minus 1 to 1/3 is -1, and so 1 minus -1 is 2, and 6. See, I got 6. Why all that? Well, all of this is for what? It's to make sure nothing weird happens. When we have improper integrals, that's not to say that, something totally bizarre is bound to happen. Actually, many improper integrals work out very, very nicely, and they work out very nicely with almost no extra help from us. But then there are other cases where things don't work out nicely. And we don't want to get into the trap where we say, things have worked out so nicely so long, they'll always work out nice, because that's when our calculus teachers, we're going to get you, right? They're going to pounce on us. And we're like, okay, we're not going to let you do that. We're just going to step back and be patient and make sure nothing strange happens. So, yes, it is true that a lot of the problems that we do, it won't feel like we did very much with improper integrals, but we will keep paying attention and say, do we need to worry about it? And if we do, let's make sure we take the steps to worry about it. If we don't, all right, good. Proceed as normal. Good. Well, let's keep going. There's lots more problems, right? Of course, there's always more problems. Okay, our next problem. Find the integral 1 to infinity of 1 over x plus arctangent of x dx. Now, our sort of initial feeling when we see something like this is like, because x plus arctangent of x in the denominator, that does not look promising. And it says find it, right? So that means we need to get an answer. Okay, so we have to think about how can we find it. Well, we see that there's an infinity involved because it's in the bounds. On the other hand, we say, look, in the range of the integral, so in other words, I should say between the bounds, 1 to infinity, I'm never dividing by 0 because it's a positive number. An arctangent of a positive number is also a positive number. So the denominator is always positive. There's no asymptotes. So the only real problem is the infinity. So one thing we can try is we can say, well, maybe this is a really bad integral. In what sense? maybe it's really infinite. I mean, that's a possibility. The nice thing about infinity is there's really not different kinds of infinity in what we're talking about. Now, depending upon how far you go, it is an interesting discussion as to how many different kinds of infinity are there. But for our purposes, there's one. And infinite means not finite. So, what to do? Well, let's think about how is this behaving. And if we can get a handle on how it's behaving, that'll pretty much say everything to us. So, look at these two pieces, x and arctangent of x. As we get large, which one matters? And by the which one matters, what I mean is, okay, which one is growing faster? Which one is getting bigger and bigger compared to the two? Well, x, it grows, but arctangent of x, it has this asymptote. So it's approaching pi over 2. So it's not getting big at all. So we say, the denominator, what does that say? So really, this is approximately x for large values of x. Because that arctangent of x, that, even though pi over 2 is not 0, if you have 1,000,000 and then you add pi over 2, it's like you have 1,000,000. You wouldn't notice an extra pi over 2. And so it's behaving in the denominator like x, which says, okay, our integral does what? Well, that's really telling us our integral, the way we think of it, it should be behaving in the long run, which is what we care about. We really don't care where we start. If you're not comfortable with saying starting near 1, all right, it's behaving like 1 over x. You can really start anywhere. There's a philosophy we're going to get to as we go into the third part of the course, which is when we're talking about infinity, we really only care what happens in the long run, or sometimes you use the phrase in the tail. And so that's just another way of saying for very large values. But what's the point? Well, the point is it looks a lot like 1 over x. And we know what happens to this integral. The integral of 1 over x gets huge. It goes off, becomes arbitrarily large. So this is infinity. So we say, aha, this feels like it should be infinite. So now we're like, woohoo, there's hope. You see, if we think the answer is infinity, that says we don't actually have to find the antiderivative. What do we need to do? Well, what we can do is say, if we can show it's bigger than something, which is infinite, then it is also infinite. So what's our plan? Our plan is make a good comparison. Now you might say, well, what do you mean by a good comparison? A comparison where I want to find something that lies underneath it and where the thing underneath gets arbitrarily large. All right, so time for us to go, So we have this function, x plus arctangent of x. Okay, so here's our function, 1 over x plus arctangent of x. And what do we want? Well, we want to have something that's even smaller than that. So here's a good rule of thumb. It's a very nice idea to remember, and it says the following. Larger denominator means what? Well, if you have a larger denominator, it means that you have a smaller number. So if I want to make my whole expression smaller, and I have like a fraction, I say, okay, make my denominator larger. Now, how are we going to use this? Well, let's think about 1 over x plus arctangent of x. The part that's making this hard to integrate, and that's making us go and ha a lot, is the arctangent. So we say, okay, let's do something to really simplify this. What can we do? Now, there's a lot of things that we can do, but I'm going to just say, hey, I know that if I think about the arctangent function, it's bounded by pi over 2. Pi over 2, it's a number, it's 1.5 dot, 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 right? It's below 2. So what we can say is the following. This is going to be greater than or equal to 1 over x plus 2. All right. See, whatever value of x you pick, because arctangent of x is lower than 2, then what's the result? Well, that says this denominator is larger than that denominator, so this value is smaller than that value. So 1 over x plus 2 is going to go in underneath. So here's 1 over x plus 2. All right, well now, what can we say? Well, because we have this nice bound, we can say the following. We have, lo and behold, our integral from 1 to infinity of 1 over x plus arctangent of x is going to be greater than or equal to 1 to infinity 1 over x plus 2. Because, think about it in terms of area. Compare the areas. See, the area of 1 over x plus 2 is this piece down here. And now, if we want to do the area 1 over x plus arctangent of x, it adds a little bit more. See, it's like that area plus even more. Well, that means it's going to be greater than or equal to. Okay, and now, what have we done? Well, what we've done is we've sort of removed the noise. And the noise was the arctangent. Say, great, this is something we can integrate. It's the natural log of x plus 2 and 1 to infinity. Of course, now we have to say plug in infinity. This is the improper part. But when we talk about plugging in, it really says, what happens as you go to infinity? So what does happen? As x goes to infinity, we're going to say, the inside is getting larger and larger, and natural log gets bigger and bigger. And therefore, it's infinity. Now, at this point, you'll say, well, are we done? We haven't actually shown this is equal to infinity, right? Well, the thing is, once you hit infinity, there's not a lot of room left. It's not like we can go, we can channel our Buzz Lightyear who goes to infinity and beyond. No, there's no beyond. Once you hit infinite, you're like, okay, it's infinite. And so what we can say is, look, it's at least infinite, but I can't get any bigger than infinite. And so, the conclusion, since it's bounded below by infinity, it must be the case that, in fact, it is exactly equal to infinity. No inequality needed. That's why infinity is special. So sometimes when you see a find problem and it looks like, what a terrible integral, maybe you can bound it by something and say, ooh, it's actually at least infinity. And you're done. Great. All right, well, that was a nice problem. It's always good when you get an arctangent of x. Wake up in the morning, you say, hey, an arctangent of x. I'm feeling pretty good about that. All right, let's look at another integral. Does the integral 1 to infinity of 2 plus sine x over x squared converge? Okay. Interesting. Well, notice it doesn't say find it. And really, it's almost a yes-no answer. So we could just guess right now and have a 50-50 chance of being right. We'd like to improve our odds to 100%, and we're going to. But remember, we're not looking for a value. We're just asking ourselves a question, does it converge? All right. Now, what's sort of the key here? Well, the key is we don't want to integrate this, which is great news. because we would have a hard time integrating this. But there's something else to see. Sine of x and cosine of x, you'll see these a lot in these types of problems. They have something really special. What's true? Well, we know how they behave, which is to say that, they oscillate up and down, right? So as you go to infinity, they keep going up and down. But they oscillate up and down in a very nice way in that they don't go too high or too low. They always stay between the values -1 and +1. So it's sort of like our great aha, our sine and cosine is bounded. So this is an important idea. Well, in fact, it's so important, we'll write it down. So aha, sine and cosine are bounded. So how do we use that? Well, let's just build it up. Sine of x is between 1 and -1. And so what we can do is, because sine is bounded, we'll say, well, let's see what happens to this expression. Let's bound that by saying, okay, let's just see worst case scenario for sine. So we're just going to start building up. We add 2 to everything. That's between 1 and 3. And now, divide everything by x squared, which is positive. Definitely we're positive. We're above 1. But of course, x squared is always greater than or equal to 0. And we don't need to worry about 0. So because I'm dividing by x squared, I don't need to worry about flipping my inequalities. So 1 over x squared is below 2 plus sine x over x squared is above 3 times 1 over x squared. So what this is saying is it says the following. And this is actually not a bad picture to have in the back of your mind. That what's happening is you have this curve, 1 over x squared. Okay, that does something like this. And then you have 3 times 1 over x squared. So it's the same curve, just shifted down. And of course, as you head off to infinity, they get closer. And what's happening is that we're going in between the two. And it really will. This function, it will bounce back and forth between the top and the bottom in some fashion. So there we are. So we've really have done what? Well, we said, hey, this really unusual function is bounded between two functions which are pretty nice. 1 over x squared and 3 times 1 over x squared are really very clean functions. So now we have to make a decision. Does it converge? For that, we look at the comparisons, right? We have something below, we have something above. If we think the answer is yes, it converges, then what we should focus on is the top. So if this converges, then, I can spell the word this, then we're happy, right? Because we're below something which converges, and that means that we also need to converge. Because converging, really you should think of it as being finite. And if we think of our integral in terms of an area, and that's how we interpret it, we say, look, the amount of area underneath this curve is below the amount of area here, and it's above 0, right? So if this is a finite number, that has to be a finite number. I can't squeeze infinitely much area into a finite amount of area. Now, on the other hand, if we think it diverges, we would say, well, let's look at something below. So if this diverges, then again, we're actually happy, right? Because it says, hey, underneath there's infinitely much area, and if there's infinitely much area down here, and I tack on a little bit more, there's still infinitely much area, and so I'm done. So it comes down to a decision. What do we think? Can we show that either this converges or this diverges? Now, if the answer to both questions is we don't know, we got to keep working. But we do know. At least we should know. What's going on here? Well, it looks like the integral of 1 over x squared. And you want to build up a sort of a repertoire, of certain integrals, whether they converge or diverge. And so one of the basic integrals is 1 over x to the p, and this will converge as long as p is sufficiently large. At least 1. Has to be strictly greater than 1. It can't be 1. Now, 1 over x squared, that would mean that this would be the case p equals 2. So we're good to go. So we say, okay, we think this converges. And so what do we have? Well, we can say, look, by comparison, we can even compare it from below, right? We can say, since the integral from 1 to infinity of 3 times 1 over x squared dx is equal to, well, this is minus 3 over x, 1 to infinity. And as we plug in infinity, okay, let x go to infinity, we'll get 0. So that's 0 minus 3 over 1. And lo and behold, we get 3. So this integral converges. So since the upper bound converges, and everything is positive here, they might say, why did you emphasize everything is positive? Well, you can imagine, like, oh, I can bound the top. Sorry, let me go this way. The top is nice and finite, but then I go really low negative, right? And I gather up infinitely much area underneath. But we can't, right? There's nowhere for it to go. So since it's bounded above by something finite, and our conclusion is it must converge. It is equal to some finite value. And there we go. Now, we don't know what that finite value is. We'll probably never know. We can, of course, get good approximations. We can, for instance, say, look, we could say, if I integrated from 1 to 1,000,000, then that would be a fairly reasonable approximation, because the tail after 1,000,000, there's not a lot of area left for it to accumulate. You can actually show very conclusively that, less, 0.000, very tiny amount left that it could possibly accumulate. Okay, 1 to 1,000,000, that's a finite integral. And now you could do numerical integration and get high precision, assuming, of course, you were very patient. If you were stuck on a desert island, if you had a lifetime supply of coconuts, you could probably make a pretty good dent in it. Of course, if you had a lifetime supply of coconuts, there's other things you could be doing as well. So, all right, well, on to more problems. Next problem. Find the integral from 0 to 2 of 1 over the square root of 2x minus x squared dx. Now, is this improper? It's actually a great question to ask. Let's think about it. If we look at our denominator, one way to think about this expression here inside is it's kind of like 2 minus x times x. Well, if x equals 0, then that's bad, right? Because that means you have a 0 downstairs. Or if x equals 2, also bad, because that means you have a 0 downstairs. So what's going to happen is that near 0 and near 2, we're going to have 1 over a small value. So what does the picture look like? Well, the picture does something along the lines of the following. So we have 0, let's say here's 2, and what'll be going on is our curve does something like this. So we're looking for this piece here. So we actually have 2 places where we could have concerns. All right, well, how to proceed? Well, for right now, we're not going to worry about the improperness until we have to, if we have to at all. Well, what do? What's our technique? We see a square root, and we're like, all right, how can we proceed with this problem? Well, when we see square roots, and we say, well, the inside is not a perfect square. We don't see like a nice substitution where it's like, oh, hey, if I make a substitution on the inside, there is sitting on the outside. That's not happening. And we do see that there's a square inside the square root. So it's like, this is looking pretty promising to think about doing trig substitution. But we can't do it yet, because remember, trig substitution says what? We need to have something squared plus or minus something squared, right? There's an expression that goes inside. So we have to rewrite it in a particular way. Now, I like to approach this by saying, let me start with this expression. I'm just going to focus on the inside. It's currently 2x minus x squared. We want to write it as either a sum of two squares or a difference of two squares. And so say, well, look, we really have sort of a start, right? There's an x squared. I'm going to factor a minus out because I really like the leading coefficient to be a 1 for the x squared, minus 2x. And now we say, well, what would we need to do? What would we need to add to make it a perfect square? Well, divide by 2 and square says if you add 1, that would be a perfect square. Aha, nice. But, of course, we can't just arbitrarily add 1. So we say, all right, well, let's just immediately balance it out. We'll subtract 1. So what happens? Well, one thing that happens, this x squared minus 2x plus 1, it becomes this value x minus 1 squared. Okay, well, that's something. Good. And so the minus 1 on the end, all right, that's a 1, and minus x minus 1 squared. So we've now written it as, here it's a difference of squares. 1 squared minus x minus 1 squared. So the variable is here. Constant squared, subtract something varying squared. All right, so updating, what do we have? We have integral 0 to 2, 1 over square root 1 minus x minus 1 squared dx. So for a squared minus u squared, the right substitution to make is set u as a sine theta. In our case, we have 1 minus x minus 1 squared. So x minus 1 should equal sine theta. All right, that's looking pretty good. And let's see what happens. Okay, well, our dx is cosine theta d theta. Okay, so that becomes the top. Cosine theta d theta. The square root of 1 minus x minus 1 squared, well, that's 1 minus sine squared. Cosine squared, square root of cosine squared, is cosine. So cosine theta over cosine theta. Now, what about our bounds? Okay, well, when we plug in 0, 0 minus 1 equals sine theta. So when does sine theta equal negative 1? Well, if we think in terms of the unit circle, our sine is our y value, so that would be at negative pi halves. So our lower bound, negative pi halves. Plug in our upper bound 2. 2 minus 1 equals sine theta. That's sine theta equals 1. That corresponds to the point there. That would be positive pi halves. So we say, wonderful. So we have that our bounds are from negative pi halves to positive pi halves. And we can clean up a little bit, right? Yeah, we can, because we can cancel the cosines. So what's our integral become? Well, our integral has now become negative pi halves to pi halves of d theta. So let's pause for a second and let's celebrate where we are. Because remember, we started by saying this is an improper integral. It's blowing up in two ends. Wow. Then we carried out a trig substitution. We were careful with our bounds. And then somehow we got to this integral. Now, is this integral an improper integral? And the answer is no. It's such a beautiful integral. It's like, wow, this is a fantastic integral. So what happened? Where did our improperness go? Well, notice the cancellation. We ended up canceling. And you see at pi over 2 and negative pi over 2, we're dividing by cosine, but you also had something upstairs. And so you got the cancellation. So essentially, the improperness canceled out. What's really being reflected here is that, hey, you're able to, when you do a substitution, it's sort of like you're changing the way you split things up in such a nice way that in this case it worked out. Now, we just finish up. It's an easy stroll to complete it. So we say, all right, this is theta from negative pi over 2 to pi over 2, which is pi over 2 minus pi over 2. Okay, so we end up with pi. What a nice answer. What a nice answer. Really clean, too. It's a really beautiful answer. All right, well, good. It just shows you, look, sometimes if you're nice, you can get your improperness will go away. Now, you might say, well, was there any place where we were being careful, but we didn't realize we were being careful? One place that we were being careful that we didn't really say out loud was really the bounds. So if you have improperness, things blowing up on the bounds, there really is this idea as we approach 0. So we could say, well, as we approach x equals 0, we're approaching negative 1. So for what angle do we approach to approach negative 1? And then we get that negative pi over 2. So in some sense, there is this sort of subtlety that we did here, but oftentimes it's very straightforward, and you can just work it, and it comes out mechanically. Things work out nicely. All right, well, let's keep going, right? More problems to do. Oh yeah. We'll be doing problems for a while. So the next one. Find the integral 1 to infinity of log of x squared plus 1 quantity squared divided by x squared dx. Okay. Well, I don't know. Let's start and see what happens. Now, of course, you might say, does it even converge, right? Before we invest a lot of time in trying to find an antiderivative and figuring out the exact value, maybe we should say, do we even expect it to be finite? So the key here is the only thing we have to worry about is the infinity. There's nothing else blowing up. Log is perfectly fine because the input for log that we have here, it's always at least 1. So log is perfectly fine with what we have. And but the other thing, the denominator only blows up at 0, and we're away from 0, right? We don't start till 1, so we're going from 1 to infinity. And so where we're at, the really only problem is the infinity in the bound. So now it comes down to saying, how do things behave? Well, we have an x squared downstairs, and then we have a log upstairs. And really, you say, look, the plus 1 doesn't really matter. And so it's like x to the 4th inside, but x to the 4th is the same as 4 log x. So you have a log x upstairs, essentially, is what you have, and an x squared downstairs. And the key thing to remember is log x grows very, very, very slowly, super slowly. And so if I think about it, well, log x over x squared, it's going to grow. Essentially, the x squared is going to dominate. And we know the integral of 1 over x squared, it's really safe. The integral of 1 over x squared is finite. So anyways, the moral is yes. There's a little bit of subtlety. One of the things that I'll say, if you go further on in math, which, hey, it's not a bad thing, right? So one of the things that turns out to be true is log of x grows very slowly. It's less than x to the epsilon for any positive epsilon. In other words, as we go out in the very, very long run, even though log of x goes to infinity, x to like the point 0.00001 will go to infinity faster than log of x will. So essentially what that says, hey, I can bound this by the integral of 1 over x to the 2 minus epsilon. Okay, that's great. I'm happy with that because I know how to integrate things like 1 over x to a power. And I know that's finite as long as my power is above 1. Okay, so we know at the start we're expecting this to be finite, so it's worth it to put in the effort. So we know we have to find it, which means there's no bounding. We're really going to have to be precise all the way through. All right, well, let's think about how we can think about this function. Now, one thing we might say, maybe there's a nice substitution, right? But I don't see a nice substitution coming out. Maybe I'm not creative enough. The thing is, if I take derivative of the inside, x plus 1 squared, it doesn't look like 1 over x squared. And so I don't think a substitution is going to be the right call. I do see that there are two pieces, and one of them involves a log. And my general rule of thumb is I really don't want to integrate logs, and because it's not so great. Differentiation, hey, I'm happy with differentiation. Logs are wonderful to differentiate. Not so great for integration. But we say, hey, there's this wonderful idea that says we could integrate a part of the integral and then differentiate the other part. The integration by parts idea. So we're like, ooh, because the log, well, we definitely want to integrate that. But 1 over x squared, hey, we're happy to integrate 1 over x squared. So let's think about this integral in the following way. I'm going to think about it as the log, and notice this exponent. I can actually pull it outside if I wanted to. So 2 log x squared plus 1, and then times this other piece, 1 over x squared dx. Okay, so we can say this first part, that's the part we're going to differentiate, and the second part is the part we're going to integrate. So the differentiation, well, okay, so we're going to have x squared plus 1 downstairs. Derivative of a natural log of something is 1 over the something. Then you put the derivative of the inside on the top, which is 2x, don't forget the times by 2. That makes it 4x, and dx. Integral of 1 over x squared is negative 1 over x. So, what do we get? Okay, this is equal to our uv. So, minus 2 natural log x squared plus 1 over x. Okay, that's our u times v. Minus, oh, and this is a definite integral, so we're going to evaluate from 1 to infinity, minus the integral v du. Now, notice they both have an x, so I can cancel the x's. I can factor out a 4 and a minus 1 outside the integral, making this a plus 4. And then we're going to have the integral of 1 over x squared plus 1 dx from 1 to infinity. All right. Well, as they say, what happens? So let's go a little bit further. So minus 2 log x squared plus 1 over x. We haven't dealt with that yet. We will in a second. And this is a nice function. It's arctangent. They were so nice to us. They gave us something that we could integrate. Okay, and we're going to go from 1 to infinity. Now we have to figure out, well, what happens when we evaluate. So let's think of our various pieces. Now, the first one, we have the infinity here. So what happens when we plug in infinity? And you'll see I do this a lot. Plug in the quote marks, right? Because we can't plug in. Infinity is not a number. But we can talk about what happens as we go to infinity. It's a process. So as we go to infinity, we say, oh, we have big thing upstairs, big thing downstairs. it's going to infinity over infinity. Which means, well, two things. Either we say, aha, I understand how growth works, or, aha, le hôpital. Oh. So let's suppose we didn't understand how growth works. Maybe we forgot that log grows much slower than x to any power. So if we forgot, okay, what would we do? Well, we would say, okay, let's say we look at the limit as x goes to infinity. The minus 2 doesn't make any difference. So I'm just going to look at this log x squared plus 1 over x. Do le hôpital, because it's currently going to infinity over infinity. That's the limit as x goes to infinity. And the root of the top, 2x over x squared plus 1. The root of the bottom is 1. Okay, well, look, it's really 2x over x squared plus 1. Now you might say, okay, what does that do? Well, we can do the L'Hopital again. Definitely not needed, but hey, why not? Limit as x goes to infinity. And again, I'm just thinking of this expression, 2x over x squared plus 1. You would get 2 over 2x. And now, say, well, 2, finite, 2x is getting huge. So it goes to 0. So, what does that say? Continuing on in our computation, that says that when we plug in infinity, so as we go to infinity, this expression here goes to 0. So we're going to get 0, subtract, plug in 1. Minus 2, log of 2, that's 1 squared plus 1 is 2, over 1. Okay, then we have to do this part, plus 4. Okay, as we go to infinity, what happens to arctangent? Well, arctangent has an asymptote of pi over 2. So it says that's going to be pi over 2. Subtract arctangent of 1. Well, arctangent of 1 is pi over 4. And now we're basically done, right? What do we have? We have 2 log 2. And if we wanted to, we could say, hey, 2 log 2, that's the same as log of 4, 2 squared. And then what happens here? Pi over 2 minus pi over 4 is pi over 4. Times 4 more leaves us with pi. So natural log of 4 plus pi. And we're done. There we go. Good. Good. All right. Well, keep going, right? Because we've got lots more problems to do. A lot more problems to do. And, well, the more we do, the better we get. So, our next integral. Find the integral 0 to infinity 2x minus 2 over x plus 1 times x squared plus 1 dx. Now, before we begin, do we expect this integral to be finite or not finite? And where's our problems? Well, you might say a -1 could be a problem, right? Well, -1 is definitely a problem for the function that we're integrating because you'd be dividing by 0. But notice, we only care what happens from 0 to infinity because those are the bounds for the integral. So look, -1, we don't need to worry about. That's fine. Okay, so what else? Well, the infinity, right? Okay, yeah, we definitely have to worry about the infinity. So, now the question is, what's happening to this function? What is it behaving like? And so there's this notion of, you might call it a limit comparison. It says, look at the rate of growth. So when you hear that phrase, limit comparison, what you're really asking the question is, how is this growing? What's the behavior like? And the way I like to think of limit comparison is get rid of the noise, and just say, what's the essence? How is the true behavior? Because oftentimes what happens when we talk about get rid of the noise, you might say, you have this one piece which is gigantic, and this other piece which is not important. So this large piece is driving the behavior. Ignore this small piece. Yes, the small piece changes the answer, but it doesn't tell you whether or not the answer is finite or infinite. It's the large piece that drives the answer to the question, am I finite or not? So, what do we do? Well, in our case, we say, hey, what happens is, look at the numerator, 2x minus 2. The minus 2, forget it. It's so unimportant. In the long run, it doesn't make a difference. So it behaves like 2x upstairs. Downstairs, these plus 1s don't make any difference in the long run. So it behaves like 2x over x cubed or 2 over x squared. So for large values of x, it's like 2 over x squared, up to a very small perturbation. And when we say a small perturbation, we say, by a constant. So I could say between 2.1x squared and 1.9x squared. That's what it boils down to. And we say, aha, and the integral of 1 over x squared as you head to infinity is finite. So we say, by looking at the growth, the way it's growing, or rather we could say decaying, because we're not getting larger, we're getting smaller, it's behaving like a function which we would expect to have a finite value. So we expect our answer should be finite. Let's hope so, right? If we get to the end and it's infinite, we're going to have to be going, oh, think of what we did. All right, well, what do we need to do here? We see that we have a polynomial over a polynomial. In other words, a rational function. So when we see a rational function, we say, let's deploy our rational function technique, also known as partial fractions. So we're going to do some partial fractions work. So let's do some partial fractions here on the side. 2x minus 2 divided by x plus 1, x squared plus 1. Okay, so it'd be, we don't have to do any division because the power upstairs is 1, the power downstairs is 3, and so it's already lower power upstairs. It's going to be something over x plus 1 plus something over x squared plus 1. Clear denominators. 2x minus 2 equals, and by clear denominators, remember that means multiply x plus 1 times x squared plus 1. We're going to get a over x plus 1 times x plus 1 times x squared plus 1. The x plus 1's cancel. So a times x squared plus 1. And we're going to get plus this expression bx plus c times x plus 1. All right, well, we now need to start choosing some good values. What are some good values? -1 is a great value. So if we plug in -1, what happens? We get minus 2 is minus 4 equals a times 2, 2a. And then here, because of that x plus 1, when we plug in -1, boom, gone. Perfect. We know that a is -2. All right. Anything else? 0 would be good, right? Because b times x. All right, plug in 0. So 0 minus 2, -2, equals a. Well, that's -2. Okay. Plus c, because the 0 times b goes away. So c times 1. Ah, c is 0. All right, great. And at this point, we're like, we've run out of good numbers. All right. Well, the good news is, even after you run out of good numbers, there's still infinitely many numbers left. There's a whole lot of them. So just pick one. And I like to pick ones that are convenient. Generally, when we talk about convenient numbers, 0 or 1, those are the most convenient. But we want it to be small, easy to work with. 2 minus 2 is 0. All right. And then we're going to get a times 2. Well, that's 2 times a. We know what 2 times a is. 2 times a is -4. Then we get b times 1 plus c. But we already know c is 0, so that's b. And 1 plus 1 is 2. So it's really 2b. Or is it not 2b? Well, no, it is 2b, right? What does that say? Well, it says b is 2. All right. So we say, aha, Ha ha ha. We know these values. So this is negative 2, this is positive 2, and that one is 0. So we get the following. This integral becomes what? The integral 0 to infinity of minus 2 over x plus 1, just copying here, plus 2x over x squared plus 1, and that's dx. Okay, well, that's not so bad. Minus 2 log of x plus 1. And here, if you look at it, 2x over x squared plus 1, that's actually kind of nice. Because if you think about it, you have a function downstairs, the top is the derivative of the function. So when you have the derivative of the function over a function, that's natural log. You could even run the substitution. U equals x squared plus 1, du is 2x dx. So this becomes natural log of x squared plus 1. And there we go, 0 to infinity. All right. Well, what happens? Well, what happens when we plug in infinity? It gets interesting, right? Because you have a minus infinity, because this is going to get large, and a positive infinity, that's going to get large. So you get a minus infinity plus infinity, which means more work. So we got to be careful. It doesn't mean that we're free. It's like, oh, I got to pay attention. Okay, so how do we do our more work? Well, they're both natural logs. When we have natural logs, we can use the tools of natural logs to simplify the expression. In our case, we say, hey, if I have a natural log and I have a constant, I can move the constant as an exponent. And if I have two natural logs combined together, say by addition, or that would make one natural log where they're multiplied, or there's a subtraction, it becomes division. So before we evaluate, let's say, hey, this is the same as natural log x squared plus 1. Since it's positive, that goes upstairs. Then I can think of the 2 as coming in as x plus 1 squared, and the minus says divide. So x plus 1 squared from 0 to infinity. Now, we can definitely do that. Now, what happens? Let's talk about 0. When you plug in 0, actually, things are nice. You get natural log of 1 over 1. Natural log of 1 is 0. So we really just have to say what happens as we go towards infinity. All right, so we're looking at the limit as we head towards infinity of the natural log of b squared plus 1 over b plus 1 squared. So if you're saying, wait, where did this come from? Well, you could think of it as we sort of said there's this intermediate stage. Limit as b goes to infinity, natural log of x squared plus 1 over x plus 1 squared, evaluate from 0 to b. And so that's what happened there. All right, now, beautiful thing, you can pass the limit through the natural log because natural log is continuous. So when you have a continuous function, limits can pass in and out of continuous functions. So this is the same as the natural log of the limit as b goes to infinity, b squared plus 1, and downstairs, if you expand it, that's really b squared plus 2b plus 1. Now, by the way, this idea that you can pass the limit in and out of a continuous function is just the idea that says continuous functions are functions where there's no surprises. In other words, what you expect to happen is what does happen. That's why you can pass limits in and out of continuous functions. Now here, we could do L'Hopital on the inside, or we could just say, hey, they both have the same rate of growth. They're both b squared. So you could say, look at the leading coefficients, and that works. Or if you want, you could say, let's push on the brakes. Slow it down, slow it down. And one way to push on the brakes is you could multiply both top and bottom on the inside by 1 over b squared. And so if you did that, you'd have log limit as b goes to infinity, of 1 plus 1 over b squared divided by 1 plus 2 over b plus 1 over b squared. So this is multiplying by 1 over b squared on the inside, both top and bottom, same as multiplying by 1. And now we're like, wow, this is great. What happens? See, look, there's 0, 0, 0. So this is going to 1. So it's going to log of 1. And log of 1 is 0. And therefore, our integral for all that work, it's 0. Wow! Now that's an amazingly nice answer. Almost too good, right? Sometimes when your answer is too good, you wonder either, how much does my calculus teacher love me? They must love me a lot. Or, did we make a mistake? What would it mean to be 0? Well, is that even reasonable? If it were 0, I'd have to be positive and negative, right? Because I'd have to get some cancellation. If we go back and look at our function, between 0 and 1, you see, it's actually a negative value. And then from 1 to infinity, it's a positive value. So it just so happens that the amount of negative value from 0 to 1, the amount of positive value from 1 all the way out to infinity are exactly enough to cancel out. And it's a beautiful coincidence. Wow, cool. All right, but 0, nice. And, well, we thought it would be finite, and 0 definitely fits the bill. 0 is about as finite as you can get, right? Hard to get much finiter. All right, our next problem. A little bit of deja vu. What? What? Didn't we just do this one? No, it's a little different, But the same ideas are going to come into play here. What are the ideas? Well, before we start, let's think about what our answer is going to be. It's kind of strange to say, before we start a problem, let's look at the answer. But when we talk about what will the answer be, what we really are after is we see it's an improper integral because of the infinity. That's going to make it improper. And when we talk about the answer, well, the question is, do we expect this to be a finite or an infinite one? Okay, so what's the rate of growth? So again, this sort of comes down to this notion of comparing, and call it limit comparison. And remember, just get rid of the noise and say, what's the real behavior? How is it changing? All right, so in the numerator, what is it changing like? Well, between the 2x and 2x squared, look, the 2x squared, much larger, that's going to dominate. Downstairs, it's behaving like x times x squared, so it's behaving times x squared. So really, it's behaving like, what? Minus 2 over x. And then we say, well, wait a second. We know something about the integral of 1 over x. 1 over x just really loses out, both as you head off towards infinity and as you head off towards 0. And so this is, we should expect an infinite answer. So why? Well, because the integral of 1 over x as you head to infinity is infinite. So we expect infinity. All right, well, let's find out if our expectations are met. So we proceed. And it's going to be very similar to what we just did. So no big surprises. We're just going to move through it. And we say, hey, we have a fraction over a fraction. A polynomial over polynomial and fraction. And partial fractions, right? And so we say, okay, do we need to do long division? No, we're good. We're great. So, all right, 2x minus 2x squared divided by x plus 1 times x squared plus 1. Well, that's something over x plus 1 plus bx plus c over x squared plus 1. All right. What do we have? Looking back at my answer, there's a negative here. So I'm going to actually update it. We expect it to be infinite, but we can even be more precise. Negative infinite, yeah. I want to get to the end. And I'll wave my hands now, then wave my hands later. Clear denominators. 2x minus 2x squared equals a times x squared plus 1 plus bx plus c times x plus 1. And of course, clearing denominators just means multiply by both sides so you don't have anything left in your denominator. Now we start making good choices. We're already taking calculus, right? So we must be making some really good choices in life if we've gone to this point. Choosing x equals minus 1. What happens? Well, we get minus 2, that's minus 4. Over here, a times 2, and here we get 0, because that x plus 1 will knock it out. So minus 4 equals 2a. All right, a is negative 2. And x equals 0 is good, because that knocks out a term there. So for x equals 0, what happens? Well, we're going to get 0 equals a, which is negative 2. Here, get c, because the b times 0 goes away, times 1. So we say, okay, c should be positive 2. And finally, plug in one more. 1 is a pretty good choice. It doesn't have to be 1. You can choose it any number you want. But remember, we love ourselves, so if you're going to choose a number, make sure you choose a number which is good to work with. So when we plug in 1, 2 minus 2 is 0. Nice. Great choice. 2a, right, because 1 squared plus 1 is 2. 2a is negative 4. And then we have b plus c. Well, c is 2, so this is b plus 2, then times 2. Well, what is that? Well, that's really negative 4 plus 2b plus 4. And the negative 4, positive 4 cancel. 2 times b has to equal 0. So we say, great, b has to equal 0. All right, wonderful. So what do we have as our pieces? Well, we have the a here, negative 2, the b, 0, and the c is positive 2. Okay, well, now we're ready to go back and keep going with our original integral. We did our partial fractions, so this becomes the integral 0 to infinity minus 2 over x plus 1 plus 2 over x squared plus 1. Well, that's not so bad. We actually know how to integrate these things. So, what is this? This is minus 2 log of x plus 1, and then integral of x squared plus 1 downstairs is arctangent. Ah, what a great integral. What a great integral. One of the top 5 integrals probably of all time. All right. Now, when you plug in 0, you get nice things. Arctangent of 0 is 0. Natural log of 1 is 0. Okay, fine. The real question is what happens as you plug in quotes, plug in, infinity. Well, we see something very different than before. See, previously we had like, oh, this part's getting to minus infinity and this part's going to plus infinity, and we're like, we don't know. But what's really going on this time? Well, natural log x plus 1, definitely that's going to blow up. It's going to get arbitrarily big. You have a minus sign. So this part's going to minus infinity. But this part, well, arctangent goes towards pi over 2. Doubling that says this goes to pi. And lo and behold, look, negative infinity plus pi is not indeterminate. We know exactly what that is. The thing is, it's really hard to compensate for negative infinity. So negative infinity plus any finite amount is still negative infinity. And so there's nothing left for us to do. It's going to go towards negative infinity. Exactly like we said it was. Wow, cool. Now you might say, wow, could we have just really done this and stopped? And it's kind of a strange answer. And I'll say, if you were more comfortable with what's going on, the answer is yes, but you need to make sure you're comfortable with what's going on. I think by the time we finish with the third part of the course, you're going to be more comfortable with this idea. For now, I think it's also important to go through the process and see, okay, things work like we expect them to work. We're trying to build intuition. You can't just have intuition handed to you. Unfortunately, that's why learning math can be hard, because you need to develop intuition, and you're like, can't you just hand it to me? No. We can give you the problems that will help you get to that point. And that's what we're doing right now, is we're doing the problems that will help you start building up that intuition. That'll help you succeed. So make sure you keep doing those problems, right? The more you do, the better you're going to be. We want you to be great. That's always our goal. That's always our goal. All right. Our next one. Find the integral 0 to infinity of e to the minus x over x dx. Okay, now notice it says find, which means we need to actually somehow get a value. Whew, all right. And now the other thing to notice is this is not looking like a very promising integral. E to the minus x over x. How do we find its antiderivative? I don't know if we can. I actually can't think of a nice way to find an antiderivative here. At least not off the top of my head. But before we invest a lot of time trying to think of various tools and techniques we can throw at this to get an antiderivative, let's ask ourselves the basic question: do we expect it to be finite? Because if we think it's not going to be finite, then we're like, hey, hold on, let's invest time to show something is infinite, because oftentimes it's a lot easier to show something is infinite than it is to determine when it's finite. And the reason, of course, is you just have to bound and show, it's at least infinite. Okay, so let's think of where are the problems. There are two of them. And so where are they? Well, certainly there's the infinity. Okay. But the other thing is there's the 0. Now, why is 0 a problem? Well, you're dividing by x, right? And so as you go to 0, it's like, oops, it's like kind of like x. Now, let's think of the two parts. Okay, so for large x, so in other words, I'm focusing right now on the top. What does this behave like? Well, we have e to the minus x over x. And one of the things that you want to do is start building up a repertoire and say, hey, I have a basic set of functions that I know how they converge. So for instance, the integral 1 to infinity of e to the minus ax dx converges as long as a is positive. And similar, integral 1 to infinity 1 over x to the p dx converges as long as p is at least 1, actually strictly greater than 1. So when we talk about for large x, we say, okay, I have e to the minus x and x, and I don't have a lot of tools to reach in. I really have two tools. What we might call this exponential, and later on you'll hear a similar thing called geometric, but that's to come, foreshadowing of things to come. And then I have this 1 over x to the p. So we have to think about things. How does it compare? Well, what really matters? In essence, we say, look, the exponential, that should be the thing that's really driving it down. It goes down to 0 a lot faster than 1 over x. And really, say, hey, that's below just e to the minus x. Because if I divide by x, and I think x is large, I'm just making things smaller. And I say, hey, that integral of e to the minus x, that's something that's going to converge. So we say, so for large x, this function is actually okay. So this would converge. So we say, okay, well, that's kind of disappointing. We were hoping it would diverge. Let's talk about for small x. So for large x, we're thinking, okay, what happens as we head off towards infinity? So for small x, the question is, what's happening as we're getting close to 0? All right. So for small x, what do we see? Well, e to the minus x over x. And now we have to sort of say, we have these two parts. How are they behaving? And if we treat them separately, like the 1 over x, okay, we know that's blowing up. What about e to the minus x? Well, when x is small, e to the minus x is like e to about 0. It's about 1. So this is really close to 1 over x. Now, one other thing I should have written down is the integral of 0 to 1 of 1 over x to p converges, and this converges when what? When p is below 1. So p equals 1, poor p equals 1, it misses out on both of these. 1 over x loses on both sides. But now we say, well, wait a second. 1 over x, that's not one of our converging things. Ooh, we say, this looks like it should diverge. We say, okay, good. So now we have kind of an idea. And you might say, wait, we do? What's our idea? What is it? What's our beautiful idea? Well, our beautiful idea is to say, aha, focus on the part with 0. In other words, the part at 0, that's the place where we think, well, we're going to show it behaves like something that diverges. Okay, and the other thing to keep in mind, if we want to show something diverges, we only have to show it's bigger than something that diverges. So this is another idea. So to show diverging, only need to show it's above. So we don't actually have to find it directly. It's above something which diverges. All right, so that's another nice idea. Wow, this problem is full of nice ideas. Fantastic, fantastic. All right, now let's start digging in. So what do we want to do? Well, we want to say we have this integral 0 to infinity of e to the minus x over x dx. The first thing we want to do is say, hey, I really want to focus on just near 1. So I don't need to worry about going from 0 to infinity. I just need to say, let's go from 0 to a little bit. So what if I threw this out? When I say throw it out, I can say, hey, think of it as two pieces. E to the minus x over x dx and 1 to infinity of e to the minus x over x dx. Now this is actually the right way to do an improper integral. Is, hey, if I have an improper integral where there's multiple problems, then I should break it up into pieces and handle each piece separately. So, okay, so that's what you can think of happening here. It's like, all right, break it into parts, and now think about each part individually, and we say, hey, we think this part is fine, because we can bound it by something which will converge. Great. So we don't want to put a lot of energy into this part. Forget it. It's going to be a waste. But we want to put a lot of energy here because if we think it diverges. So can we drop this? The answer is yes. Why can we drop it? Well, remember, I just need to show it's bigger than it. It's above something. This part, because it's never negative, whatever the answer is, it's at least 0. So if I drop this, that's greater than or equal to the integral of 0 to 1 of e to the minus x over x dx. All right. That's kind of our first idea. Focus just in on just the part near 0. We're going to need another idea. So our second idea says, okay, now that I'm focusing near 0, I need to say, hey, I really just want to focus on the 1 over x, because I really want to make this just something which is easy to do. So I want to somehow rewrite the e to the minus x. So let's think about our function e to the minus x. We're going to do a little bit of note here on the side. So our e to the minus x is doing this. I'm only going from 0 to 1. Now, what do I want? I want to say it's bigger than or equal to something. So at 0, I'm at the value 1. And at 1, where are we? Well, we're at the value of 1 over e. So what's true is that e to the minus x is bigger than or equal to 1 over e for 0 less than or equal to x less than or equal to 1. In other words, I'm just saying, look, pick out the smallest value. We're just trying to get an upper bound. So remember, we don't have to get it exact. We just say, look, it's bigger than or equal to that. And what we want to do is we want to say, somehow take out the things which are unpleasant. Remove them so that what's left is really simple to work with. It's the beautiful thing of calculus. Always try to make things easier because, like I said, we care about ourselves. We really want to make sure things are easier. And so we're getting rid of the part that's not the problem. So we say, hey, this part is bigger than or equal to the integral 0 to 1 of, I can replace the top by 1 over e over x dx. So this is the idea that we have here. By the way, this also shows why we need to cut down. Why didn't we just say, 0 to infinity e to the minus x? Why did we have to do this, break it up from 0 to 1? Well, notice what happens to e to the minus x. In the long run, it's going to go to 0. So I would only be able to say e to the minus x is bigger than or equal to 0. That's not helpful at all. Because then we say, it's bigger than or equal to 0. Forget it. That tells us nothing. We don't want to have something that tells us nothing. We want to have some information. All right, but now that we've got rid of that e to the minus x, we say, this is beautiful. We can integrate. This is 1 over e natural log x from 0 to 1. Now, of course, it's improper, but we'll handle that. Natural log of 1 is 0. So you get 0, subtract. Now, the improperness we'll handle by talking it out loud. We have a problem at 0. So we have to say, well, what happens as we go to 0? Because you can't plug 0 into natural log. As you go to 0, natural log does the following. It goes down to negative infinity. So 0 minus infinity. In other words, it's diverging. And so that says this integral is infinite. Now just follow the inequalities. The integral that we started with, 0 to infinity of e to the minus x over x dx, is bigger than or equal to infinity. There's not a lot of space left. As soon as you're at least as big as infinity, you're infinite. So we're done. It's infinity. Good. Now, this has some subtleties. This is not one of those things where you wake up after the first time hearing about improper integrals and say, these are all obvious things. Aha! But the more you play with things, you like to say, okay, what matters? What doesn't matter? Break it into parts. Okay, what's happening with each part? What can we do? How can we simplify the integrals? These are important ideas, and the more that you work the problems, the more natural the ideas start to become. All right, well, still more problems to do. Oh yeah, there's still more problems to do. Plenty of time, right? Plenty of time. An infinitely deep well filled with grape juice, originally the problem was filled with wine, but we changed it to grape juice, is formed in the shape resulting from spinning the curve y equals log of x for 0 less than or x less than equal to 1 around the y-axis. Okay, wow, what a shape here. All right, so yeah, you see, what do you have? What's not drawn here is the y-axis. So this is the y-axis here. Whoop! And here's the x-axis. And so we're taking this shape and we're spinning. So, okay, great. What are we going to do? Well, keep going. The well is completely full. Wow, that's an infinitely deep well full of wine. Now, grape juice, remember? Okay. Now you might say, got to change that. Grape juice. I thought we got all the changes. Okay. And it has a density of 50 pounds per cubic foot. Determine the amount of work it will take to empty the well. In other words, how much work will it take to bring all the grape juice up to ground level, and include units in your final answer. Now you might pause and say, is this realistic? You're talking about some infinitely deep well. I mean, even though the earth is pretty big, it's not infinitely deep. Does this make sense? And the response is, well, of course, this is all a thought experiment in some sense. But it's not unreasonable to use infinity to represent very big. And so even though, yes, from a standpoint of we could never have it be infinitely deep, you can imagine, well, it's a very, very deep, and so we'll have infinity be a natural stand-in for saying, okay, just very deep. It's similar to in business. You always want to assume, like, look, your business will be open forever. As soon as you say, hey, we're going to assume that our business is going to shut down in X number of years, it causes lots of problems in your business plan. So, there are reasons to say, let's think of things as going on forever. All right, well, what's our problem? What type of problem do we have? We see it's going to be a couple of things. First off, we see infinitely deep. Okay, so that tells us, hey, there's something improper going on. But we also see this word here, work. You say, aha, it's work, and so it's about, it's a pumping problem, where we pump some fluid out, and we're trying to ask the question, well, how much work does it take to empty it? So we say, all right, we have to think about what's the setup. Well, how do we do work problems like this? The idea is say, hey, I'm going to come down to some height, and I'm just going to take this little piece and pump it up to ground level. Now, how do we know we're pumping it up to ground level? Well, because it says bring it up to ground level. That was our big clue. So, how do we proceed? Well, let's start with our basic formula. So work is adding up, start to finish, and then we're going to have our individual pieces. We're going to have our distance, how far we have to move our little piece. We're going to have our density, how dense is our fluid at that place. We're going to also have to have a volume, and the volume is going to be an area and then a thickness. So this is the basic formula for work. We've done this before. And we start thinking about, okay, we really should have things all expressed in terms of y. So y equals log of x, that's actually the wrong thing to have. So how do we get rid of the log? Well, exponential. So we can say, oh, this is x equals e to the y. So how do we proceed? Well, this would be the integral. Where do we go from? Well, from ground level down all the way, right? So we're going between minus infinity to 0. What's our distance? Well, we want to go from this level y up to the level 0. So what is that? Well, it would be negative y. All right, you have to be careful here, right? You want to say, wait, isn't it y? Well, pay attention, because y's are negative down here. And when we talk about a distance, it's a positive amount. So if you don't like negative y, think of it as 0 minus y. Where we have to pump up to, subtract where we currently are. The density, 50. All right. The area. Now, this is formed by revolution, which means it's a circle. So we're going to have a pi times our radius squared. Well, what's our radius? Well, our radius is this distance from the axis to where we're spinning around. So it's the x-coordinate. So our x-coordinate at a particular height y is e to the y, and of course squared, and then we have a dy. So that's our setup. Okay, great, good. Well, that's not so bad. We could even do this one. Okay, so let's see what we have. I'm going to move this up here just for space reasons. I can factor out the 50 and the pi. Those are constants, also the negative. So minus 50 pi integral from minus infinity up to 0 of y, and e to the y squared would be e to the 2y dy. All right, wonderful, wonderful. So what happens next? Well, for this, we say, okay, what's the right technique? We see y, e to the 2y, and we say, this is something that's a little bit partially hard, right? Now, it's integration by parts, right? Okay, so maybe we should do a little bit of work down to the side here. So if we do y, e to the 2y, we're not going to worry about bounds here. Well, we say, look, the y, if we make that our u, that helps drive it down, so we'll make dv the other part. And then what happens? Well, then what we get, let's see, we can move this up a little bit. We'll say, okay, du is dy, and v is 1/2 e to the 2y. So this becomes uv 1/2 y e to the 2y, and then, okay, minus the integral of v to u. So there's a half integral e to the 2y dy. Okay, so that's 1/2 y e to the 2y, and this integral, bring out another 2, so minus 1/4 e to the 2y, and plus c. Okay, so we can do that integral by parts. It's not a bad integral to do. So, picking up where we were, this becomes negative 50 pi, and this expression here, 1/2 y e to the 2y minus 1/4 e to the 2y, and evaluate from minus infinity to 0. So, plug in 0. You have minus 50 pi, then you'll get 0 here because of that 0, and you'll have minus 1/4 times e to the 0, which is 1. Okay, subtract. Now, the hard part. Well, maybe not the hard part. I mean, there's a couple of non-trivial steps here. There's the how do you set this problem up, make sure you remember work, the integration by parts. The last sort of non-trivial thing is handling what happens at the improper part, the infinity. Now, part of it we can see right away. I have e to a large negative number. That's going to go to 0. Okay, good. The other part, I have y e to the 2y. And I'm going to negative infinity. Well, what happens? Well, there's two pieces. There's the y part, and then there's the e to the 2y part. This y part, it's getting huge. This e to the 2y part, because it's a negative number, right? It's getting small. So I have polynomial growth, exponential decay. So who wins? In a race between polynomial versus exponential, which one comes out as the dominant term? Now, if you know the answer to that, then we're done. And if you don't, well, we have to figure it out what the answer is. I'll tell you the answer. If you're looking at the question of which one wins between polynomial versus exponential, exponential always beats polynomial. So what's going to happen is that this part will go to 0 as well. So let's suppose we'll take that as a given. We'll take a look at y in just a second here. And then we'll say, perfect. Look, that goes away. Minus minus makes a plus. And I can even take 4 and divide into 50. Well, I can at least divide. I can get 25 pi over 2. Now, it did say units. Well, okay. We know the units for work because our measurements here are in feet and pounds. So we see pounds, we see feet, so forth and so on. And so we're going to have 25 pi foot-pounds. And that's our, 25 pi over 2 foot-pounds. That's our answer. It's kind of amazing, right? Because if you think about it, we have this infinitely deep well, which means that we have to get some of that grape juice and pull it up from an almost, it's not, we can't pull it from infinitely deep, but arbitrarily deep. We're still pulling out grape juice, even all the way down. And yet, it's still a finite amount of work. It's this beautiful idea that says, yes, you might be adding up infinitely much, but you still have a finite thing in the end. It's a beautiful, beautiful idea. Now, let's spend a few seconds figuring out why is it the case that between y and e to 2y that we're going to have the e to 2y dominate, and in other words, we're going to go to 0. Well, okay, so if we think about it, we have big, we think of it as going to infinity, small going to 0. That's indeterminate. When we have indeterminates, we like to do l'Hopital. And the first step of doing l'Hopital is try to write it as a nice fraction. So we could say one way to write limit as y goes to infinity, minus infinity, y e to 2y is the limit as y goes to minus infinity of, I'll move the e to the 2y downstairs. So it's e to the minus 2y. So now they're both getting big. Taking the derivatives, since they both go into infinity, we can apply l'Hopital. We say, aha, this is the limit as y goes to minus infinity of 1 over minus 2 e to the minus 2y. And we see now, wow, look, the denominator is getting huge because y is negative, so it's e to a large positive number downstairs. So that's 0. And this is sort of the whole reason about why is it that polynomial loses out to exponential. If you look at it when you do l'Hopital, no matter how many times you hit the exponential function with the derivative, it sort of says, I'm still here. I might pull down a constant, but it's like, yeah, I'm still exponential. But when you do that derivative with the polynomial, the power starts dropping, and eventually the power gets down so low, it's like, well, all right, I'm out, and I'm done. So that's why polynomials lose out to exponentials. Okay, and there we go. Good. Now we know how to get out our grape juice. And fun problem. Good. It's nice to be able to do applications. All right, well, let's try another application, right? If it's so fun, we should keep doing them. Of course it's fun. All right. Find a positive. So the length of the polar curve, r equals e to the minus a theta, where theta goes from 0 to infinity, has length 13/5. Now, you'll notice they graphed part of it. It actually spins infinitely often around. But of course, as I spin around, I'm moving very close. So I'm actually moving pretty quickly towards the center. So even though I'm going to make infinitely many circles, I'm still going to have a finite total length. At least that's the claim. And the other thing you might notice, 13/5 is not just sort of a random number. You'll see there's certain numbers that show up very frequently in math. And that's because you have what are called the Pythagorean triples. And so certain numbers that show up a little bit more often, especially anything that might involve a square root, and distance at its heart is a square root. There's the classic 3, 4, 5, but right behind that is the 5, 12, 13. So that says that there's a triangle where you have one side of length 5, one side of length 12, and the hypotenuse is length 13. 5 squared plus 12 squared equals 13 squared. So when you see numbers like 13 and 5 together, you're like, ooh, there might be a 12 popping up in our answer. Maybe. Maybe. All right. So what do? Well, we actually can spot a lot of the things that we need to do. We see length and polar curve. I'll say, all right, so this is a problem which involves length of polar curves. We just have to remember what's the formula for that. And so the formula for r equals f of theta, where our theta runs between two angles, it's the length. It's a really beautiful formula. You add up from alpha to beta the square root of the original function squared plus the derivative of the function squared d theta. So for us, what does this become? Well, we're going from 0 to infinity. That's the improper part, the fact that there's this infinite process happening. And then we're going to have the square root of, and this is our function, so e to the minus a theta squared plus, now take the derivative. And what do we have? Well, we're going to have the minus a comes down, e to the minus a theta squared d theta. Well, that's actually not so bad as integrals go, because what's happening? Well, you'll notice that both of these terms have e to the minus 2a theta. So you could pull that out, and then you have a 1 and an a squared. All right, great. And hey, the square root, you can take the square root of the first and the square root of the second, and the square root of 1 plus a squared does not depend on theta, so that can go all the way out, square root of 1 plus a squared, and then integral 0 to infinity, e to the minus a theta d theta. Beautiful, beautiful. Okay, well, when we integrate, what do we get? Well, we have the square root, 1 plus a squared, and then the integral of e to the minus a theta. Well, that's e to the minus a theta divided by negative a. Now, we know a is positive, by the way. So just a side note, a is positive. And we're going to go from 0 to infinity. Now, plug in. We plug in infinity, which means what happens as we go to infinity. As we go to infinity, we're going to have a very large negative number up here in our exponent. And e to a large negative number is going to be small, go to 0. So this is going to be 0, subtract. When we plug in 0, okay, e to 0 is 1. So we have a square root of 1 plus a squared over negative a. Or if you like, that's the square root of 1 plus a squared over a. And we know our total length is 13 over 5. All right, so now our goal is solve. And so we say, okay, what can we do? Well, let's start by squaring everything. If we square both sides, what would we have? Well, we would have the following. We'd have 1 plus a squared over a squared equals 169, which is 13 squared, over 25. Now, notice 1 over a squared plus a squared. What's another way to write that? Well, you can write it as 1 over a squared, right, plus a squared over a squared, which is plus 1. Okay, so we say, hey, that tells us something. 1 over a squared is 169 over 25. Subtract 1. Well, I can think of subtract 1 as being subtract 25 25ths. which would make this 144 over 25. Okay, well now we really are really close. We have a single a, flip both sides, and we see, a squared equals 25 over 144. Take the square root, and remember, a is positive, so I don't need to worry about plus or minus. Square root of 25 is 5, and the square root of 144 is 12. 5 twelfths. Hey, 5, 12, 13. Coincidence? No. As I say, when you see numbers like 5 and 12, or 12 and 13, or 5 and 13 come together, you should be like, I think they're trying to pull a little Pythagorean triangle in here. Good. And then we'll be ready. And, of course, once you're ready, we're good to go. All right. Well, keep going, right? More problems. Lots more fun to do. Okay, on to another problem. Good. Well, what's the next one? Rotate the region bounded by 0 to x to infinity and 0 to y to e to the minus x squared around the y-axis. And, what's the volume? Find the volume. Well, let's get a sketch here. Now, e to the minus x squared is kind of a famous curve. It's called the bell curve, and it's used in statistics very extensively, so it's a very well-studied function in some sense. And so what do we look like? Well, we go down, and we do something like that. All right, so we have this basic region where we're going from x to 0 to infinity and y from 0 to the curve. So there's our region here. And now we're going to spin it. And of course, you always want to pay attention which axis are you spinning around, because of course, depending upon which axis, you might have a reasonable answer or an impossible task. In this case, we're going to spin it around the y-axis. Okay, so how to proceed? Well, we're doing volume revolution, and we know there's actually multiple ways to do it. There's, generally speaking, 2 ways to do it. So one of the first things to decide is how. What's the right technique to use? Now, the way I like to approach these problems is I say, okay, well, it's given to us as a function of x. So let's just assume we're integrating with respect to x, which means when we think of slicing, that would be our slice. So as we spin around, what do we form? Whatever the slice does will dictate our technique. And we see here, we're forming a shell. And so we're like, aha, shell method. Okay, good. So now we know not only are we looking for volume, but we know the way we're going to look for volume is by the shell method. So how does the shell method work? It's good to remind ourselves. This is quite the review. We're doing all these problems, remembering so many useful things. So the shell method says, add up, start to finish. You have a 2 pi, and you have a radius, a height, and a thickness. So when we talk about these pieces here, the radius, how far from where you're spinning, so this is your radius. Your height, how far up and down do you go? Your thickness is that little piece right there. I'll put a little tiny delta. That's your thickness. So that's our formula. Let's just fill in, and we'll see where we are. So we know we're going from 0 to infinity. It was told to us, 0 to infinity. So we have integral 0 to infinity. And then we have 2 pi. Our radius, well, we're going from an x to 0. So our radius is x. Our height, well, e to the minus x squared. And our thickness, dx. All right, that's not looking too bad at all. And indeed, we say, hey, this is not too bad, because if you think about it, look, there's an x squared, but there's also 2x. And one of the things that we start to develop is like, hey, the x squared, the root of that is 2x. Oh, I see. It's setting us up for a nice substitution. Woohoo! They are nice to us. So you say, all right, let's proceed that. Let's follow that trail that they left for us. U equals x squared. Du is 2x dx. We say, all right, perfect. What would this do? Well, let's do the bounds. And of course, you have to think about bounds. Whenever you have an improper integral, you got to be careful with the bounds. The improperness is the infinity. And we say, okay, 0 is no problem, so 0 squared is 0. The infinity, so when we put infinity here, it says, as we go to infinity. So, as x goes to infinity, what's happening to x squared? It also is going to infinity. All right, great. So, then we have a pi. Nothing happened to that. 2x dx became du. And then e to the minus x squared is e to the minus u. All right, wonderful, wonderful. Well, this is a very straightforward integral. Minus pi e to the minus u. And evaluate from 0 to infinity. And of course, when we plug in, we really say what happens as we go to. So as we go to infinity, we have e to a large negative number, which is 0. Subtract, plug in 0, well, we're going to get minus pi times e to 0, which is 1. So we end up with pi. We're done. Wow, wow, what a beautiful, beautiful answer. So we say, aha, the integral of e to the minus x squared, when we spin this around, gets us to pi. And this actually, there's some very interesting mathematics that comes into this, which we'll touch on in multivariable calculus. So keep going, right? We're getting there. We're getting there. You know, multivariable calculus, it's the fun part. Wait, I thought this was fun. Okay, it's all fun. It's all fun parts. All right, well, let's keep going on to our next problem. Find the integral 1 to infinity of 1 over t log of e squared times t log of e to the fourth times t dt. And kind of our reaction is, what? Okay, wow, well, okay, we're going to find it. Now, you might say, hey, maybe it's infinite, right? Because we've done some of those in this session where we're like, hey, it's actually turns out to be an infinite value. And it's not a bad gut feeling, right? Because it's like, look, it's a 1 over t. The integral of 1 over t as we go from 1 to infinity is infinite. But notice, it's not just 1 over t. There's some little extra pieces here. These pieces are log of t. So what does that do? Well, it really pushes the curve down a little bit. Now you might say, does it push it down enough? We don't know yet. And we're going to have to play around and think about it. It might just be enough. So we're going to try to figure it out. All right. So what can we do? One thing we can do is we say log of e squared times t is just such a strange thing to write. Because what could you do with that? We could rewrite this in the following way. See, this is the same as log of e squared plus log of t. In other words, multiplication becomes addition, and log of e squared becomes 2. Now you might say, well, wait a second. Why did you bother to do the separation first? Why don't you just pull the 2 down, right, as 2 log of e times t? And the answer is you can't do that. Here's why. Look at this. We'll do it with the e to the 4t. I can't pull this exponent down by itself because it's only on part of the expression, right? It's only attached to the e. It has to be log of the whole thing raised to a power. If it's only a part of it raised to power, forget it. Forget it. You can't apply the rule. So that says that this part becomes 2 plus log t. Same process, right? Break it by addition, bring the 4 down. The other part becomes 4 plus log t. All right, well, okay. That certainly looks nicer, but is it an improvement? Well, let's see where we're at. So we have 1 to infinity, 1 over t, 2 plus log t, and 4 plus log t dt. Now, the next thing is to say, oh, log of t, we see that, and we see a 1 over t. Now, why is that nice to see? Well, the derivative of natural log of t is 1 over t. So in other words, we see the derivative of log of t sitting right there. It's beckoning with its siren wail, substitute me, substitute. We'll listen to it this time because it looks like a pretty straightforward substitution. So we'll let u equal natural log of t, then du becomes 1 over t dt. Wow, perfect, 1 over t dt, that's great. So this becomes integral. Well, 1 over t dt becomes our du, and so I'll write as 1. We have a 2 plus u, and a 4 plus u, and a du. Now, what about our bounds? Well, natural log of 1 is 0, so that's a 0. How about the upper bound? Now, of course, when we talk about infinity, we're really saying as we go to infinity. So our upper bound is as t goes to infinity. So we say, okay, so to figure out what happens, we say, well, what happens to u as t goes to infinity? And the answer is goes to infinity. Natural log goes to infinity very slowly, but it gets there. It gets there. And say, okay, all right. So really what they were doing is they were kind of obfuscating this. This looks more reasonable, right? This often happens in problems where they're like, hey, there's this somewhat reasonable problem. Let me masquerade it, hide it away, so it looks like something that's like hopeless, like, ah! But we're not going to be scared off at the start. We say, we know what to do. We know how to solve this. All right, well, from here, we see this is partial fractions. So we're going to do our partial fraction setup. 1 over 2 plus u. 4 plus u is something over 2 plus u plus something over 4 plus u. Clear your denominators. 1 is a times 4 plus u plus b times 2 plus u. All right, choose wisely. Whereas the good choice brings you closer to the answer, a bad choice takes us further from it. In our case, well, u equals negative 2, great choice, right? Because that would knock out the second term. So we get 1 is equal to 2a. All right, that says a should be a half. What's another choice? Well, negative 4 is another choice, right? Because that will knock out that term. What does that tell us? 1 equals 2 minus 4 is minus 2b. So b is minus a half. All right, so there we go. A is positive a half, b is negative a half. And we get updating, so integral 0 to infinity. So we have a half over 2 plus u, so write it as a half, times 1 over 2 plus u. And then b is minus a half, so I'll write it as minus a half, 1 over 4 plus u, and du. All right, well, these are great integrals to work with. So this becomes 1/2 integral of 1 over 2 plus u is log of u plus 2. And then minus a half log of u plus 4. I could have put 2 plus u and 4 plus u. Same thing. And we have to evaluate from 0 to infinity. Now, we can, of course, combine these together. So this is the same as 1/2 natural log of, the top would be u plus 2, and the bottom would be u plus 4. Right? Yes, it is. All right, great. Well, the last thing to do is, of course, evaluate, because this is evaluate from 0 to infinity. Now, we've done a couple of these, so we're just going to be a little bit more relaxed, or friendly here. What happens as we go to infinity? So as we go to infinity, well, the inside, that's the only place where u shows up, we have u plus 2 over u plus 4. That's going to go to 1. Look at the leading coefficients. So this is going to be 1/2 log of 1. That's what happens as we go to infinity, which really says it's going to go to 0. Subtract 1/2 log, and now, plugging 0, 2 over 4 of 1/2. All right, so our answer is minus 1/2 log of 1/2. And that's it, right? We're done. Well, we are done. Now, it's kind of an unsatisfying answer, because we said, wait a second, negative? That's a negative value? That looks pretty positive to me. Everything here in the denominator is positive. How did we end up with a negative as the answer? Here's the secret. We didn't end up with a negative as the answer. Yes, there is a negative there, but it turns out log of 1/2 is itself negative. Now, one thing you can do if you don't like negatives, it turns out log of 1/2 is equal to minus log 2. You can think of it as 2 to the minus 1 power, and then bring the minus 1 power out. So if you don't want to write it as a negative, this is also equal to 1/2 log 2. And there you go. Now, you might be wondering, okay, you're doing lots of integrals, but it doesn't feel like you're doing a lot about improper integrals. And where are you handling the improperness? And so the key thing is, we say, just make sure there's no problems other than, make sure there's only one problem per integral, right? There's only one infinity involved. And we should have pointed out, look, this is never going to be 0 in the denominator from 1 to infinity. And so we're fine. The only problem is the infinity. So there's only one infinite. And the place we handled it was in this step here. This is where we handled the infinity. We said, okay, what's happening as we go to infinity? There was a sort of implicit limit. And in our case, we said, well, we can see it without having to resort to limits. If we had needed to, we could put a limit down. Sure, if we needed it. But in this case, we were okay. And in many cases, we are. All right, well, let's keep going. More problems. There's always more problems, right? Okay. Our next problem. Find the integral from negative infinity to 0 of e to the power 3t over 4 minus et to the power 3/2. Oh, all right. Well, this is interesting. This is, what's this going to be? Now, you might say, okay, we can spot something going on here. There's definitely an infinity involved. All right, that's great. We might get a little bit nervous and be like, oh, what about down there? So let's think about what's happening just to calm our nerves, because it's good to have our nerves be calmed. When we look at this function e to the 2t, and we're thinking in particular between negative infinity and 0, so we're in that range between negative infinity and 0, what's going to happen? Well, as we head to negative infinity, e to the 2t goes to 0. As we head to 0, it goes to 1. So this quantity, this e to the 2t, is only going to be between 0 and 1. So if we take 4, subtract that, we're actually in pretty good shape because it's not blowing up. So, okay. So we're okay. We're okay. So this is nothing wrong. The only real challenge is the infinity. So you say, okay, all right, well, let's proceed. How do we proceed in this problem? Looking at this, what do we see? Well, we see something that looks like a square root, and there's not really an obvious substitution to make. At least not one that I think would be clean. And so what can we do instead? Well, one thing we can do is we can say, hey, it looks like a square root, and one way to deal with square roots is partial fractions. Can we think of this as a difference of squares or as a sum of squares? And we can, right? Because look, this is 2 squared, and e to the 2t is a secret way to write e to the t squared. And similar, e to the 3t is a secret way to write e to the t cubed. And so oftentimes when you see like e to a constant t, what's happening is that it's obfuscating the fact that it's really e to the t to a power. It's one of those things that, calculus teachers love to do on homeworks and quizzes and exams. We're telling you all our secrets because please learn. We want you to learn everything. We really do. Okay, so picking back up. Whenever we see an a squared minus u squared, our substitution to make is u equals a sine theta. Now in our case, 2 squared minus e to the t squared says, hey, the right substitution to make is e to the t is 2 sine theta. So now we just have to sort of work through what's going on. So e to the t dt is 2 cosine theta d theta. All right, that's not so bad. Well, what else? The square root of 4 minus e to the 2t. Well, what's going to happen? It's going to be 4 minus 4 sine squared. And so you can pull out the 4, that makes it a 2. And square root of 1 minus sine squared becomes square root of cosine squared. So cosine theta. All right, well that's great. Okay, so what do we get? Okay, so we're going to get an integral. The e to the t cubed, one of the e to the t's is going to join with the e to the t dt. So there's really this e to the t cubed is e to the t squared e to the t, right? So we have an e to the t dt. That's going to join and make a 2 cosine theta d theta. Okay, so that's 2 cosine theta d theta. We still have, I didn't give myself enough room. All right, there's a d theta over here. We still have to do that e to the t quantity squared. So e to the t is 2 sine theta squared. There we go. All right, well, great. Okay, so that's e to the t dt, e to the t squared, divide by, well, that's the square root of 4 minus e to the t cubed, all right, to the 3/2 power. So that's 2 cosine theta cubed. All right. Now, are we done? Have we gotten everything? No, not yet. We haven't gotten our bounds, so we've got to do our bounds. Okay, so let's work on the bounds, because this is oftentimes working on the bounds is when you handle the improperness, whenever you do some kind of a substitution. So, as we go to negative infinity, well, what's happening? We have to think about what our pieces do. The e to the t goes to 0, so what we're looking for is 1 to 0 equal 2 sine theta. Well, that really says 1 to sine theta equals 0, and that happens at 0. Okay. And how about 0? Well, what's that going to do? Well, at 0, we have e to the 0, 1. 1 equals 2 sine theta. Okay, that says sine of theta is a half. And aha, that is a nice angle. Do you remember it? When does sine equal a half? It's at pi 6. So 0 to pi 6. There we go. All right, well, let's clean up a little bit here and see what happens. Now, we have a bunch of 2 cosine thetas, so we can knock off one from upstairs with one downstairs. You'll notice that we have 2 squared and 2 squared, so that gets knocked off. And then we have a sine squared over a cosine squared. And we say, wow, this is really becoming nice. So what do we end up with? We end up with integral 0 to pi over 6 of tangent squared. Now, at this point, you'll notice no longer improper. See, the improperness went away when we changed our bound. So the improperness was handled when we talked about what happens when we go from, negative infinity to 0. There we go. That's the right one. So that's how we handled the improperness. So there was it wasn't done like, we're going to pretend like nothing happens. No, we paid attention. Well, let's finish it up. How do you integrate tangent squared? Well, by rewriting it. See, tangent squared is the same as secant squared minus 1. All right, well, great. That's on our list of things we know how to integrate. Tangent theta minus theta. And we just go from 0 to pi over 6. So, when you plug in 0, good news, 0. Tangent of 0 is 0. 0 is 0. When you plug in pi over 6, well, you get tangent of pi over 6, subtract pi over 6. And tangent of pi over 6 is an angle we actually know. We can compute the tangent of that. It's 1/3 times the square root of 3. So 1/3 times the square root of 3 minus pi over 6. And we're done. We're done. Wow, kind of a nice answer. Of course, anytime we get an answer, it's always a nice answer, right? Any integral you can walk away from is a good integral. Isn't that how they say it? I don't know. Well, at any rate, we continue on. More to do, more to do. Okay, our next problem. Find all the b that are positive such that the integral from 1 to infinity of b divided by x squared plus b squared dx is 1. Okay, so we want to find all the positive b where this is true. So, okay, we can see, why is this an improper integral? Well, because, again, there's an infinity involved. All right, so certainly there's an improperness, but really it says, hey, we now give you the answer. What was the problem? This is kind of one of those fun, hey, let's turn things around. And when we do that, it's really do we understand the process? So this should be fun. I always like these kinds of problems that sort of like, hey, let's turn things around. Can we still solve it? And if the answer is yes, we're like, woohoo, yeah. All right, so, what do we do? Well, suppose we look at this integral and we say, okay, if we had the integral of b over x squared plus b squared, let's just think about that integral. I'm not going to worry about bounds for the second and say, what could we do? I mean, what does it remind us of? It feels very arctangent-y, doesn't it? Well, it is very arctangent-y, right? Because like 1 over x squared plus 1 is an arctangent. So we can approach it in a kind of a similar vein. So even though it doesn't look like a trig substitution problem, we can still use trig substitution here. So trig substitution really is a great way to help deal with plus signs. At its core, that's a goal of trig substitution. How can I deal with plus signs? So we can make a substitution, and in particular, b tangent theta. Then what we get is that dx would be b secant squared theta d theta. All right, That's not so bad. And x squared plus b squared, well, would it be what? B squared tangent squared plus b squared. And you can pull out a b squared, and tangent squared plus 1 is secant squared. Ah, nice. Nice. Ah, cool. So this integral becomes the following. Well, we have the dx, we have the b here, and then there's a b secant squared theta, d theta. Downstairs, well, the x squared plus b squared becomes b squared secant squared theta. And then we look and say, whoa, nice. The b squareds cancel, the secant squareds cancel, which means it's the integral of d theta, which says, hey, that's theta. So we say, well, what is theta? Okay, so we start and say, let's solve for it. Tangent of theta would be x divided by b. So that says that theta is arctangent of x over b. And so therefore, this becomes, the answer is arctangent of x over b. All right. Now that's if we did an improper integral. Now we'll go ahead and throw it in as a proper integral. And let's see what we get. Okay, so our integral 1 to infinity of b over x squared plus b squared dx. Remember, that equals 1. We'll come back to that. That's equal to, according to what we just did, arctangent of x over b, evaluate from 1 to infinity. Now, of course, here's where we handle the improperness. We can't just plug in infinity, but we can ask the question, what's happening as we go to infinity? As we go to infinity, we see, okay, it's arctangent of a big number because b is positive, so x over b is going to be positive big. So it's going to get large. All right. Arctangent has an asymptote, and so it approaches pi over 2. Okay, so that's as we go to infinity. We've handled the improper part. Subtract arctangent of 1 over b. Okay, so great. Remember that equals 1. So we can swap the 1 and the arctangent of 1 over b. And what do we get? Well, that says arctangent of 1 over b is equal to pi halves minus 1. Okay, now our goal is to solve for b. Now, so get rid of the arctangent. Well, we can do it by taking the tangent of both sides. 1 over b is equal to tangent of pi halves minus 1. And now we can flip things over. So that says b. If you flip tangent over, that's not inverse tangent, right? It's 1 over tangent. 1 over tangent has another name. It's called cotangent. All right. There we go. That's our answer. But we can actually make it look a little bit nicer. And, okay, so how can we make it look nicer? All right. Here's a fun fact. This is equal to tangent of 1. And that's also the answer. These two are equal to each other. So let's talk about why. And it really comes down to just thinking about a triangle. And so if you have an angle alpha here, we'll call this angle beta. What are those angles? Well, they're complementary angles. And so oftentimes if alpha runs into beta, alpha might say, beta, you're looking fantastic today. Have you lost weight? And beta might say, alpha, is that a new hat? It is perfect for you. They're close friends, always giving each other compliments. So what happens here, what does that have to do with anything? Well, what we can say is if we think about the cotangent of alpha, what would that be? It's its opposite side to its adjacent side. Sorry, cotangent is the adjacent to the opposite. So cotangent of alpha is adjacent to opposite. Well, the tangent of beta is its opposite to its adjacent. In other words, it's the same ratio. So when I have complementary angles, then there's this nice relationship going on. In essence, you can think of that's where the co is from the complement of the tangent. So how do we use that? Well, notice what happens. Well, what if our angle is 1? So if we make alpha 1, then beta, the complement around a space, is pi halves minus 1. So these two angles are complements to each other, and so I can swap out. So that's how we get to our answer. What a really clean answer. It's almost too good, right? It's like, wow. Now you might be saying, hey, can we replace tangent 1 by something? And no, tangent 1 is just tangent of 1. There's not a nice value. Of course, we can always get a numerical value, but for us, that's all we need to do. And we're done. Good. Well, I think we've been at it for a while. Let's do one more. One last problem, a cool down. All right, well, it might be a little bit more than just a cool down. So, find the integral from 1 to infinity of 1 over x cubed plus 1 dx. Now, we can do integrals like 1 over x plus 1. We can do that one really easily and say that diverges. 1 over x squared plus 1. That one's also pretty straightforward because it's arctangent. Great. 1 over x cubed plus 1. Now, you might say, well, wait, does x cubed plus 1 have any vertical asymptotes we need to worry about? It does have a vertical asymptote at -1, but we don't need to worry about it because we only care about from 1 to infinity. So the vertical asymptote, it's far away, no problem. All right. Do we expect it to be a finite integral? In other words, are we actually going to have to put work in? Well, the short answer is yes, right? Because think about it. For large values of x, it's basically like 1 over x cubed. And we know that the integral of 1 over x cubed is finite. So this integral will also be finite. Okay, so how do we start? All right, some of the things that we're about to do are maybe not the most obvious, and it does require a little bit of algebra, but it's nice to do a little bit of algebra every now and then. We know our basic approach. This is a rational function. What does that mean? Polynomial over polynomial. So we're going to do this rational function problem, which is partial fractions. So let's go through our partial fractions process. Do we need to do long division? No, we're already set. What comes next? Well, the next thing is to factor. Now you might say, well, maybe x cubed plus 1 doesn't factor any farther, but here's a wonderful true fact. Every polynomial is factorable, and this is more of a theoretical than practical, but it still is a true statement, as a product of what are called linear terms, things like x plus or minus a number, and irreducible quadratics, things like maybe x squared plus ax plus b, where there can't be factored down into linear terms. So you can always get down to that point. Okay, so that means that there's some factoring to be done. And the majority of the work on this problem is going to happen in the setup. So here we go. How do we factor this? Well, notice that this is the same as x cubed plus 1 cubed. In other words, it's a sum of cubes. And so there's a formula from algebra that says, hey, there's a way to handle a sum of cubes. So the formula says if you have a cubed plus b cubed, you'd have a plus b, so x plus 1. and then you'd have x squared minus x and a plus 1. Now, that's if you remember your algebra. There's a couple things you could do if you didn't remember algebra. You could say, do I know a root? And in our case, we could say, well, -1 is a root, right? Because -1 cubed plus 1 equals 0. So if you know a root, that says you know a factor. -1 being a root means x plus 1 is a factor. Okay, so now you know you can pull out an x plus 1. And how do you get the rest? Well, you can get the rest by long division. So if you take x plus 1 divided into x cubed plus 1, you'd get x squared minus x plus 1. Or you can remember the sum of cubes formula. You can verify that it works, right? Just sort of go through it. So x times x squared is the x cubed. Then you have a minus x squared and a plus x squared, which cancels. A plus x and a minus x, which cancels. And a plus 1. All right, so it works out. All right, well, now partial fractions. This is equal to, we have a over x plus 1, and this is an irreducible quadratic. And I won't go into why just right now, but it will come up in a little bit. In one way to see it's an irreducible quadratic is set it equal to 0 and solve. And if you try to find the roots, you'll see if you just say the quadratic formula, you get complex numbers. And when you get complex numbers, that's what we mean by irreducible. Complex numbers means it cannot be factored using only the real numbers. So we are going to have a bx plus c over x squared minus x plus 1. All right, clear denominators. So we get that 1 is equal to a times x squared minus x plus 1 plus bx plus c times x plus 1. All right, well, let's choose values. And if we choose well, it's not going to be too bad. If we choose x equals -1, what do we see? Well, the last term goes away, 0. Minus 1 squared is 1. Minus 1, 1. And 1 is 1. So you get 1 is equal to 3a. Or a is 1/3. If we choose x equals 0, well, what do we have? We get 1 equals a times 0 minus 0 plus 1. So that's a, but we know what a is. A is 1/3. And then plus b times 0 is 0 plus c. So that's c times 1. Okay, so that says c is 2/3. All right, well, we know a, we know c, which says we just need to figure out b. So pick any number. Well, let's pick 1, right? 1's a nice number. Okay, so what happens? 1, we get 1 minus 1 plus 1 is 1 times a. So that's a, that's 1/3. Plus b plus 2/3. And then 1 plus 1 is 2. Well, okay, so what can we do? Well, if you subtract 1/3 and divide by 2, that tells you that b plus 2/3. So if you subtract, that's 2/3 divided by 2 is 1/3. Or you can say, hey, that says that subtracting 2/3, b is minus 1/3. All right, so b is minus 1/3. So now we're pretty happy. We say, wonderful, we have our partial fractions decompositions, right? So we get, this is 1/3 x plus 1, and then we have plus a minus 1/3 x plus a 2/3 over x squared minus x plus 1. All right. Now, here's where things are going to get interesting. You're probably thinking, wow, Steve, it's already interesting. We don't need to make it more interesting, do we? Oh, well, we should always make it more interesting, right? It's better than less interesting. So the question becomes, how do you handle something like this second piece? Some constant x plus some constant over x squared minus x plus 1. That's the hard part to handle. If we know how to handle that, then the rest won't be so bad. Okay, so we have to think about it. Now, the thing that makes it maybe a little bit challenging is that minus x. For a second, suppose it wasn't there. So you saw like an x squared and a plus 1. We would say, oh, well, that's no problem. That first part would be, if we covered it up, it would look like an arctangent. And if we covered up that second part, it would look like a log. Okay. And so in general, that's what happens. You're either going to have an arctangent or you're going to have a log. And it just depends. So we want to have that same thing going on as we go forward. So we're going to keep rewriting this with an eye towards getting to the point where our integration won't be bad. So we're putting in a lot of prep work so that at the end we're like, and ta-da! So this is laying the groundwork for good stuff down the road. Okay, so now we're going to spend some more time really digging into this x squared minus x plus 1. So this would be x squared minus x. I really want to make it a perfect square. So what would I need to add? Well, divide the middle term by 2, minus a half, square it, would be a fourth. If I want to get to plus 1, I get 3/4, right? So x squared minus x plus 1, x squared minus x plus the fourth plus 3/4, which is x minus a half squared plus 3/4. Right? Cool. Fantastic. So, how is this going to help us? Well, the key here is to say, I really want to make the upstairs look like x minus a half. That's going to be our key as we go forward. So, let's keep rewriting. So what do we have? We have, this is the 1/3 times x plus 1 and plus, well, let's go ahead and factor a third out, right? Because both of the terms have a third. And downstairs we have x minus a half squared plus 3/4. And upstairs, well, we've pulled out the third, so it's the minus the x. And here's the way we're going to say, I don't want to think of that as x. I'm going to think of that as x minus a half plus a half. Right? Because if I minus a half plus a half, that's just 0. And of course, then of course there's I haven't forgotten, there's a plus 2 on the end. All right, so what do we have? This is the first term. Well, let's go ahead and pull that 1/3 down. So 1/3, 1 over x plus 1. And now there's still this 1/3. And here in the exponent, we have minus x minus a half. And notice what you have. You have minus a half plus 2. Minus a half plus 2 would be what? 3/2. So plus 3/2. And that's over x minus a half squared plus 3/4. All right. Well, this is actually good. We're doing great. And I know it feels very strange, but we're making good progress. So the last thing is I just want to sort of split it up into pieces. So we're going to have the 1/3, 1 over x plus 1. And this is an easy integral. We should have said from the beginning, look, this part we're happy with. It's the other part where we want to really break it up. So this last part, okay, we're going to break it up the subtraction. So minus 1/3, and then we're going to have x minus a half over x minus a half squared plus 3/4. And then 1/3 times 3/2 is 1/2. 1 over x minus 1/2 squared plus 3/4. All right, so this is partial fractions where we just pulled the things apart, and then we worked on our irreducible quadratic, even separated that just a little bit further so that we could help set ourselves up for success. On a side note, this part right here, we could, if we wanted to, rewrite it. This is x squared minus x plus 1. We could go back. Now, notice our pieces here. Take the derivative of x squared minus x plus 1. What would you get? 2x minus 1, which is 2 times x minus 1/2. So what you have is you set up so that in this first piece, you have a function downstairs and derivative up to some constant upstairs, natural log. Here, you have 1 over variable squared plus something squared, number squared. That's an arctangent. So now we have ways to handle each piece. All right, well, we still have to handle each piece. So we're not going to fit it on one page. This is going to be a 2-page problem. Wow, that means it must be twice as good as other problems. Okay, so let's just move this up temporarily. And we have the integral 1 to infinity of 1 over x cubed plus 1 dx is equal to, I'm going to use the partial fraction decomposition. That's going to be 1/3, don't forget the integral, 1 to infinity of 1 over x plus 1 minus 1/3 and x minus 1/2 over x squared minus x plus 1 plus 1/2 1 over x minus 1/2 squared plus 3/4 dx. Okay, there we go. Whew, nice, nice. Well, time to start chipping away. Okay, so we have our little pieces, and let's just work through them one at a time. So this first piece, well, that's no problem. That, when we integrate, well, we're going to get the integral 1/3 of 1 over x plus 1 dx. That's 1/3 natural log x plus 1. Okay, so that one we feel pretty good about. All right, well, there's still some other pieces though. Okay, let's go to our middle piece, number 2. So for this part, what do we have? Well, we have integral minus 1/3, and there's the x minus 1/2 over x squared minus x plus 1. And the point was, by rewriting it, by making it look like x minus 1/2, we're setting it up so we have function downstairs, derivative upstairs. So we would do our substitution, u equals x squared minus x plus 1. du is 2x minus 1 dx. And now we say, oh, well look, divide by 2. 1/2 du would be x minus 1/2 dx. We say, great. So what do we have? This is the integral minus 1/3, then there's 1/2, so that's minus 1/6. And then there's the du, okay, that's the x minus 1/2 dx, and over u, which is minus 1/6 log u. But of course, we can replace it. Minus 1/6 log x squared minus x plus 1. All right, good. Well, 2 down, 1 to go. So now we and work on our next one. So here, what are we going to do? Well, this is set up for arctangent. Like, it looks like arctangent, right? 1 over variable squared plus number squared. So we're like, perfect, ha, arctangent. So we got to just do our substitution. So we talk about the integral 1/2, and we have 1 over x minus 1/2 squared plus 3/4. Hard to write everything in here, but right, we have u squared plus a squared. Well, a would be square root of 3 over 2. So our substitution would be x minus 1/2 is our u equals a, which would be the square root of 3/4. That's square root of 3 over 2 times tangent. All right, well, dx becomes square root of 3 over 2 secant squared d theta. All right, now, well, where do we go from here? We carry it out, right? So we have the half. The dx makes it a square root of 3 over 2. And then there's a secant squared theta, d theta. And downstairs, well, we have 3/4 times secant squared, 3/4 times tangent squared plus 3/4. Now, the point here is to say, hey, look, this is really 3/4 times secant squared. So we say, beautiful. Once we have that, the secant squareds cancel. Pew! We can even get the 4 to cancel with the 2 1/2. And so what we really have, after we've done all of that, we have that square root of 3, and there's a 3 there. So this becomes square root of 3 over 3, and then integral of d theta, which is theta plus c. And so we say, all right, last thing, well, what is theta? Well, that's the square root of 3 over 3. You'd multiply across 2 over root 3 and take the arctangent. So arctangent of 2 over root 3 times x minus 1/2. All right, good. Whew. All right, now we've done actually all the calculus. We've done every piece. We've integrated every single piece. So what we need to do now is we put it all together and do our evaluation, and then we'll be done. So we add. We get 1/3 natural log of x plus 1 minus 1/6 natural log x squared minus x plus 1, and then add square root of 3 over 3 arctangent of 2 over root 3 times x minus 1/2. And that's our antiderivative. Evaluate from 1 to infinity. All right, and off to the races. So what are we going to get? What are we going to get? Well, let's start with the infinity. Almost makes you want to start with the 1. No, come on. We need to do both of these. How do we plug it in? Well, the arctangent, really that's going to be okay, because as we let x go to infinity, okay, the inside gets large, arctangent heads towards its asymptote, it approaches pi over 2. So this part we're fine with. We're happy with that part. The first part, well, this is getting big. This is getting big as well, but they're being subtracted. It's an infinity minus an infinity. Okay, well, when you see infinity minus infinity, that means more work. There's more work to be done. So how do we handle that? Well, here's where we can say, well, let's use the power of natural logs to combine. So maybe before we evaluate, let's think about what we could do. Let's pull out a 1/6. So this is 1/6. Then you have 2 natural log of x plus 1. subtract natural log of x squared minus x plus 1. All right, now the key here is subtraction corresponds to division. Constants become exponents. So this becomes 1/6 natural log of x plus 1 squared over x squared minus x plus 1. Or if you like, 1/6 natural log of x squared plus 2x plus 1 over x squared minus x plus 1. All right. Well, that was a lot to put there, but that's what we were going to get. Now, it's not so bad. Okay, so when we plug in infinity, what's going to happen? Of course, plug in as we go to infinity. What do we get? Well, here we say, look, notice we can push to the inside. As x goes to infinity, you have x squared over x squared. Those are the leading terms. The inside goes to 1. So we get 1/6 log of 1, which is 0. So the log terms are gone. Nice. Ah, okay, now what happens here? Well, this is getting large, we've talked about before, so this is going to pi over 2. So we get square root of 3 over 3 times pi over 2. So that's when we plug in infinity. Now plug in 1. Okay, when you plug in 1, well, actually, let's just see it right here, right? So we're going to subtract. We can plug it in here. 1 plus 1 squared, that's 2 squared, that's 4. 1 minus 1 plus 1, 0, gone. So we get 1/6 log of 4. That's it. We could actually have done it here. It's the same as 1/3 log of 2, because you're going to get 1 minus 1 plus 1 is 1 is 0. So that's 1/3 log 2 sounds better than 1/6 log 4. So 1/3 log 2. And now, plug in 1. What do we see? Well, we have 1 minus a half. That's a half times 2 over root 3. So we have root 3 over 3 arctangent of 1 over root 3. Well, can we find arctangent of 1 over root 3? Turns out we can. It's actually a nice angle. So the angle where the output of tangent is 1 over root 3 is pi over 6. So minus a root 3 over 3 times pi, it's a plus, be careful here, pi over 6. The minus comes from the minus there. Well, look, here's a root 3 over 3 times pi over 2, a root 3 over 3 times pi over 6. So, all right, pi over 2, subtract pi over 6. Well, that's 3 pi over 6. Subtract pi over 6. That ends up being 2 pi over 6, which is pi over 3. So pi over 2 subtract pi over 6 is pi over 3 times root 3 over 3 makes it a root 3 over 9 times pi, and then a minus a 1/3 log 2. Done. Done. Oh, wow. It's cool we can get an answer, but it goes to show you, like, just even a little bit, it's like, oh, and it's like, wow, it becomes very, very much more interesting. One might say a little bit more challenging, but the processes are okay, and you have to just be careful. The only place where we really needed to handle the improperness was at the evaluation, and well, we had to handle that. It was not trivial there, right? Because you had an infinity minus an infinity, but we found a way to work around that, and so we got it to work out. Well, all right, that was a lot of practice, but learning to deal with infinity is a very nice thing to do, and very important. And so I'm glad we did the practice at least once, right? And good. Well, keep going. Lots of fun stuff right around the corner. So I hope to see you again soon.